will be repetition, but as I say all the time, that is intentional and very much by design so that you hear a little bit of duplication so the content is that much more familiar to you for both lecture and for lab. Okay, so let me see what's here. Oops. Okay, can you guys hear me now?
Yes, I can.
Yes.
Okay, outstanding. I just wanted to make sure. All right, outstanding. So all right, so we're going to pick up with blood today, and start the chapter 17, and it's really going to be a lot more about blood than you probably thought you ever needed to know. But there's going to be 4 extra credit questions. Again, you'll send those to me at the end of the class within 15 minutes of lecture ending, and I will award you extra credit, and that will verify that you were here in attendance. Okay, so we'll go ahead after today with blood. We have next week, Tuesday and Thursday only, those 2 lectures, and it's time for our first break, our first study day, and then first exam already. So the semester is moving pretty rapidly. Let's go ahead and talk about blood for a minute. So some of this is going to be very obvious, things that you guys already know. Some of it will certainly be new, like I said. We're going to dive into how blood cells form, for example. So blood obviously is a transport medium, first and foremost, a part of the cardiovascular system. We'll be talking a lot more about blood and its role in the cardiovascular system later on in the course, in the next unit. But there are 3 primary functions of blood. Beyond transportation, and by transportation, we typically think of oxygen, right? But also regulation and protection. And these next couple of slides, and you can see that that's underlined, so make sure to understand that blood is an important component of our body to both transport and regulate and protect. And you'll see why in the coming couple of slides. All right, so like I said, transportation is pretty obvious, right? We think of delivering oxygen. Our cells, our tissues, our organs need oxygen more than they need anything else. Without the delivery of oxygen from our red blood cells, our cells would start to shut down very rapidly and we wouldn't be long behind it, okay? Beyond that, we also have all the nutrients, the carbohydrates, the fats, the proteins that we ingest in our food and our beverages, any kinds of enzymes and ions and other things and proteins that all get transported by blood, because transport, if you recall back to Bio 210, is a form of connective tissue in that it has the unique ability to connect to everywhere in the body. Okay, so it's very unique that unlike any other tissue type, it reaches everywhere. So it's perfect for delivering oxygen and nutrients. Beyond delivering quality products like oxygen and nutrients and enzymes, it also removes the trash, okay? Metabolic waste, okay? Carbon dioxide is the one that comes to mind a lot, right? That when blood hits the lungs, it's oxygenated and then it's pumped out through the body, and that oxygen is dropped off at the cellular level, and the cells, in the process of their activity, cellular respiration, protein synthesis, mitosis, etc., they, much like a factory, they produce those products and they require oxygen and ATP for fuel, but they also accumulate waste. And carbon dioxide is the principal waste that our cells produce in day-to-day activities. So that gets offloaded into the bloodstream, onto the erythrocytes, our red blood cells, which then are pumped back to the lungs and we exhale, and that carbon dioxide is eliminated from the body. So transport of both good quality products in and waste out. We just talked about the last 2 lectures about the transportation of hormones. We certainly know about that, but almost everything is transported by the cardiovascular system attached to one form or another of a blood cell. So that's transport, again, a little bit more intuitive. Regulation, when I think of what does our blood do to regulate? the thing that pops in my mind is blood pH, and you can see that that's highlighted. We'll talk a little bit more about pH levels and just how sensitive and how narrow the bandwidth is for a healthy blood pH. Okay, we're extremely sensitive in the range of acid or base that we can survive and thrive in. Okay, so that's the first regulatory aspect of blood. But body temperature is another one that's pretty obvious. If it's freezing cold and we walk outside, our capillaries of our extremities near the surface area will constrict. They'll get small and they'll drive that blood inward to our core to keep that blood from being near the surface area, from near the skin, to absorb the cold and keep us warm. Okay, another example. We've talked about fluid volume levels and how they relate to blood pressure, specifically water and plasma as being key components of blood volume. Again, this is another regulatory function of blood and the receptors in our vasculature. And then we go to protection. Protection, the first one is protecting from losing too much blood. And we'll be talking about that again later in the class when we talk about quantities of blood loss before it becomes threatening. But certainly we have clotting mechanisms that are there to fix any damage that is incurred. So our cardiovascular system, in a sense, protects itself by having these platelets and fibrin and fibrinogen floating around in our bloodstream, ready to lay down a clot should we need it if there's some type of trauma. Okay, beyond that, prevention, and we'll be talking more about these things next week when we talk about the lymphatic system and immunity, but we're going to be talking about antibodies and our leukocytes, our protective warrior cells that are out patrolling our bloodstream, watching for pathogens, bacteria, viruses, cancers, any type of toxins that we inhale or ingest. Our immune system is out there circulating in our cardiovascular system, in our blood, trying to identify rapidly any threats that are foreign to the body, and then ideally trying to eradicate them before they act, before they take hold and become consequential. So several layers of protection that blood offers us as well. All right, so the basic characteristics of blood, you guys know most of this already. Obviously, blood has a sticky compensation to it with a metallic taste due to the iron concentration in the hemoglobin found in our body, in our blood rather. It is, again, the only tissue type that is liquid in nature. And again, it's classified and falls into that connective tissue category that we studied in depth back in Bio 210. The color of blood varies depending whether it's oxygen rich or whether it's oxygen depleted. So if our blood is exiting the lungs and the heart, headed out toward the cells of the body, and has oxygen on board, it's going to tend to be a brighter color red. The oxygen presence tends to lighten up the shade of red a little bit. And then after the oxygen has been dropped off systemically out at the cellular level in the body, and carbon dioxide waste is loaded on instead, it kind of changes its tint a little bit and becomes a darker red. Okay, back to what I mentioned about pH. And if you ever want to appreciate how sensitive and amazing your body is as far as survivability goes, and also just consider for a second how fragile we are. If you remember back to basic science, again, back to Bio 210, we talked about chemistry very briefly. A absolute neutral pH level on a pH scale is 7. The scale goes from 0 up to 14. Anything from below 7, as you move 7 down toward 0, is becoming more and more of an acid. And as you move from 7 up toward 14, it becomes more of a base or more of an alkaline. Okay. Our blood as humans, the average normal range is about 7.4. So we're slightly alkaline oriented, a little bit of a base. But you can see the healthy range, and you can see that this is underlined. So you'll definitely want to remember these numbers for your exam, that the survivability and thrivability, very small bandwidth again, that we can survive in, is only 7.35 to 7.45. Okay. So that tiny, tiny 1/10 of a percent, outside of that, either direction, our organs will shut down due to what's called either alkalosis or acidosis. And of course, once our organs shut down, we're not far behind it. Okay. So very, very sensitive when it comes to pH in our bloodstream, and those receptors being fantastic at what they do, and noting slight disruptions to homeostasis and making adjustments to correct for and restore that average range of 7.4, so we can continue to exist despite all kinds of different threats and things that we ingest. Average volume of blood, about 5 liters of blood in an adult. We all know what a liter bottle of soda looks like. So you can imagine what 5 liters would look like. This kind of shows, and it's a little bit inaccurate, that males have around 5 to 6 liters of blood and females have 4 to 5. The reason for those disparities in numbers is based on average body size. Okay. So that's a very generalized statement there based on gender. It really should say based on body size. Okay. If there's a larger female and a smaller male, those numbers could be exactly the opposite. Okay. But just remember, about 5 liters of blood in an adult for capacity.
What's taking his light so long?
Okay. Whoops. Alexis. Alexis, we're not
Yeah.
interested in what's keeping the light so long. Okay. Guys, that's the last warning. From now on, you guys are going to get dropped from the Zoom. I'm not doing this. This is like kindergarten with this group. I teach more remote classes than anyone else. This is the only sections that can't seem to remember one simple thing: mute your microphones. No one wants to be disrupted, least of all me. New policy as of right now. If your mic is unmuted for other than a call, and hear me close, you're going to be dropped from the Zoom first time. Second time, you lose the ability to earn extra credit for the entire semester. I'm serious. I don't deserve to be disrespected like this from people not being attentive enough to simply look at your computer and mute your microphone. It's ridiculous. All right. I can change real fast, guys. I've done it previous semesters. I can take all this underlying content away. I can just teach every single thing and tell every one of you, learn it all. Good luck to you. And I'll do it. Grow up. All right, one last shot. This slide, I was about to tell you before being rudely interrupted that this slide is one of your 3 lecture exam matching questions. Okay, guys, this is a matching question. In fact, it's literally this slide. Okay, so that's why this whole thing is highlighted like this. Be prepared for this to be, there are 3 matching questions on exam number 1. Be prepared to take a look at this slide, and especially at this test tube, after the blood has been taken as a blood sample, went through the centrifuge, has been spun out and divided, where the different elements of blood, the components, separate themselves from one another, and be prepared to identify these different points here, okay? They're really easy matching questions if you're prepared for it. So that's why I wanted to share this with you, so you guys can be prepared and never be surprised on an exam, okay? So when we talk about whole blood, all right, once we spin it in the centrifuge, and again, we've talked about this and introduced this in lab previously, but 45% of blood are what we call the formed elements, okay? The erythrocytes are our red blood cells, and they are essentially the entire 45%, okay? The erythrocytes by far are the most in number, okay? The leukocytes and the platelets make up less than 1% of blood, okay? So 45% are the formed elements, almost exclusively erythrocytes. Then that leaves about 55% of whole blood, if you divide it and spit it out, is blood plasma, the liquid portion of blood, okay? And again, we've talked about that over in lab. That should be a recap, but I wanted to highlight it one more time, just so you guys can be absolutely sure and confident to do well on that matching question for exam number 1. All right, so this complements exactly what I just said. Whole blood is comprised of the liquid portion, plasma, which, by the way, is about 90% water, and then the formed elements, the erythrocytes, the leukocytes, and the platelets, okay? There are also solutes, and as the slide says, over 100 different types of solutes, like electrolytes and proteins, for example. Different chemicals that are a part of our blood. They're dissolved in our blood, they're transported by our blood. And when we talked about the endocrine system, we talked about many of these already. Things like sodium and potassium and calcium, right? You certainly remember this from Bio 210 with sodium potassium pumps, for example. Okay, bicarbonate as an important regulator of blood pH, like we just talked about, different ions. Okay, all of these things, of course, are transported from cell to cell, from organ to organ, via the bloodstream. Okay, and then we have proteins. Okay, they're by far the largest of the solutes. They do not enter into our cells, and the largest or the most frequently occurring plasma-borne protein is called albumin, and you can see that that's important to know for the exam. Albumin is about 60%, a little bit more than half of all of the plasma proteins, okay? And albumin, like many other proteins, is produced and made by the liver, okay? And it's an important buffer. And if you remember back to Bio 210 in chemistry, that buffers minimize or slow down, delay a chemical reaction. And if you recall what we just talked about blood pH and the extremely sensitive range that we can survive in, we understand why a buffer like albumin would be very, very important, right? We sure don't want a wild radical swing in our blood pH. We'd be in trouble very fast, okay? So albumin, being a larger molecule and being about 60% of plasma protein, contributes, and all of the proteins do for that matter, toward the osmotic pressure of plasma, If you remember, osmotic pressure has to do with the density, the thickness of it, determining which direction a fluid would leave, in or out of a capillary. So that's what these underlined statements here are saying that I want you to make sure you're familiar with and understand for the exam. All right, some other solutes. We have some waste products. We've talked already about carbon dioxide, but things like urea, which is a waste product from breaking down proteins at the cellular level, uric acid, which is a waste product from breaking down nucleic acids out in the tissues. Then our nutrients that we ingest that I've mentioned, and we'll be talking a lot when we talk about metabolism and the digestive system, carbohydrates, fats, proteins. Once they're digested by the digestive system and reabsorbed into the bloodstream, they have to be circulated to the individual cells, right? So that our cells can use them, our muscles can use them as fuel, as energy. Okay, respiratory gases, this is predominantly, again, our oxygen and carbon dioxide. And as we've talked about for the last 2 lectures, our hormones have to get around the body, and blood, of course, and our plasma specifically is one of the mechanisms in which they do that. First of your 4 quiz questions for today. So remembering what I said about the average normal pH range for blood in human beings, which of those answers? Write them down and you will email those to me at the end of the lecture. All right. So carrying on. All right, so this slide looks a lot like what we already talked about over in lab. Microscopic images, histology slides of blood cells, and specifically those formed elements, the erythrocytes, the leukocytes, and the platelets. The erythrocytes are real easy to tell. First of all, they're going to be by far the most numerous, as we saw, because less than 1% are platelets and leukocytes, all right? They're typically displayed as being red or pink in color with a little bit of white in the center, and that's because they're biconcave shape, meaning they're almost like a donut if the hole in the middle didn't quite go all the way through, okay? The reason that erythrocytes are concave shaped on both sides is to increase their surface area. If you increase the surface area of the erythrocyte, they have more oxygen carrying capacity. Okay, so hence the shape. What we're seeing on histology slides when you look at an erythrocyte is the light being able to shine through that paper thin center part because they're indented or concave on both sides. It's kind of paper thin, so the light from the microscope can shine through, and that's why they appear to be kind of have a white circle in the middle of the erythrocytes. The leukocytes kind of stand out. They're typically much larger. They stain with purples, whether they're granular or non-granular, doesn't really matter. They tend to jump out on the histology slide. And then the platelets are just these tiny little dots, these little protein fragments floating around in the plasma, okay? So pretty easy to differentiate all 3 types of formed elements if you're looking at a histology slide. And trust me, for sure, over in lab, you're gonna have to do that. All right, so we talked about the formed elements previously. Again, erythrocytes, leukocytes, and platelets. Not going to talk about this in depth again because we've done it in lab. I've already done it here in lecture today, but I want to go ahead and point out, just because it's going to be on the exam, that the erythrocytes are those red blood cells. Again, these are our carriers of oxygen to the cells and carbon dioxide away from the cells. Know and remember that erythrocytes are the most prominent, meaning they have the most of them of the formed elements. They're about 45% of whole blood, okay? All right, so how do we form these formed elements? Where do they come from? Okay, the process is called hematopoiesis, okay? Hematopoiesis is the formation of any of the blood cell types: erythrocytes, leukocytes, or platelets. Okay. They all occur in the red bone marrow. Okay. And if you remember back to Bio 210, when we learned about bones, the red bone marrow, that spongy red bone area in the trabeculae, is at the distal ends of our long bones, like our femur and our humerus, also found in our flat bones between the two plates, like in our cranium, in our bones of our pelvis, in our sternum. Okay, that's where red bone marrow is. It's in those red bone marrow type areas where hematopoiesis, or the formation of blood cells, occurs. Okay, now, whenever we're forming a new cell, we need a stem cell that kickstarts it all. Okay, and the analogy of a stem cell is almost like an acorn for an oak tree. Okay, in order to have something like an oak tree, you have to have a seed first, right? In this case, with an oak tree, it's an acorn. In the human body, in order to have new muscle tissue or new smooth tissue for stomach lining, you need a stem cell of that variety to give rise to what the end product is going to be, to develop and to evolve into it. Okay. And when we're talking about hematopoiesis and the formation of blood cells, we're talking about a hemocytoblast. And you can see that that's underlined. So know that a hemocytoblast is a hemopoietic stem cell. Okay. And these hemocytoblasts are going to give rise to the formed elements: erythrocytes, leukocytes, and platelets. Now, interestingly, one hemocytoblast can become any one of the three of the formed elements. Okay, when they first start, they aren't differentiated. So they could turn into an erythrocyte, a leukocyte, or a platelet, depending on what the body needs and what stimulus is going on. Once they make up their mind and commit, though, to being an erythrocyte, for example, they can't change their mind and halfway through the process evolve into a leukocyte. Okay, so just understand that a hemocytoblast is the stem cell that goes through the process called hematopoiesis, a forming of one of the three formed elements. As a hemocytoblast, it has the capacity to be any one of the three, and once they've committed, they can't change. The erythrocytes, talked about these before, and here you can see an illustration of that biconcave nature that again allows them to be much thinner in the middle, to appear on a microscope slide to have kind of a white center. Again, the erythrocytes carry gases, okay? Oxygen to the cells, carbon dioxide away from the cells. All right. What's interesting and different about erythrocytes is that they do not have a nucleus and they don't have organelles. So they don't have a mitochondria or ribosomes or endoplasmic reticulum and any of the organelles that we learned about when we talked about other cells. They are, however, filled with a gas called hemoglobin. Okay. And hemoglobin is about 97% of the volume of an erythrocyte. Okay, so they really fill up and comprise what an erythrocyte is. And the best way to understand what hemoglobin does inside of an erythrocyte rather, is to act almost like a magnet. Okay, hemoglobin has a magnetic bonding relationship with oxygen. So when that erythrocyte is at the lung level, the oxygen that's coming in from the air that we've inhaled is going to jump off of the alveoli in our lungs and bind to the hemoglobin within the erythrocyte. Then it's going to get carried on that erythrocyte out through the body, and at whatever stop it makes along the way at the cellular level, that hemoglobin is actually going to flip, and we'll talk more about this later on in the respiratory system. And it's going to, much like a magnet can do, it's going to now push the oxygen molecule off of the erythrocyte into the cell. Okay, so at the lung, it acted like a magnet to pull the oxygen molecules onto the erythrocyte and hold on to them as they're being transported. And then at the cellular level, it changes and the hemoglobin works to eject the oxygen off of the erythrocyte. And then at the same time, forms a magnetic bond for carbon dioxide and pulls the carbon dioxide on to carry and remove the waste away back to the lungs. Okay. Even though for oxygen, almost all oxygen is carried on erythrocytes, only a small percentage of carbon dioxide is actually carried on erythrocytes. Most of it is in the blood plasma, as we'll see in the next slide. All right, so there's different terms for where the hemoglobin and the erythrocyte is in the cycle, where the red blood cell is, okay? So when the blood becomes oxygenated in the lungs, so now we have oxygen attached to the hemoglobin. It again, like we said earlier, becomes a brighter shade of red, and it's called oxyhemoglobin because they're bound together. Out at the cellular level, when the oxygen exits off of the red blood cell into the tissue, it becomes deoxygenated. So now its terminology changes to deoxyhemoglobin and takes on that darker red shade that I mentioned earlier. Then, once carbon dioxide, waste product, jumps on, technically at that point, it changes its name to yet a third variety called carbaminohemoglobin. Okay, so it just depends what's going on with that hemoglobin and what's attached to it at the time. It either has oxygen attached and then it's oxyhemoglobin. If it has nothing attached for that brief moment, it's deoxyhemoglobin. And then once carbon dioxide is attached, then it's carbaminohemoglobin. Okay, and here's where that statement that I made on the previous slide holds up, that only about 20% of carbon dioxide coming from the cells as waste product actually binds to the hemoglobin. The rest dissolves in our blood plasma, that liquid portion, and makes its way back to the lungs in that manner. Second in your quiz questions today. So what are the most commonly or most numerous formed elements seen in blood? All right, continuing. All right, so let's talk about erythropoiesis, okay? The formation of red blood cells, okay? Erythropoietin is a hormone that we didn't spend a lot of time, in fact, we didn't talk about it at all in lab, other than that it was mentioned in the fetal pig dissection as being a hormone released by the kidneys. Okay, that is very true. And like she mentioned in that video, not only is erythropoietin a hormone released by the kidneys, there are hormones released by the heart, there are other hormones that we didn't touch on in our discussion of the endocrine system. What we did in Bio 211 is talked about the most prominent hormones and the glands of the endocrine system, but there are others, erythropoietin being one of these. All right, so erythropoietin is a hormone that circulates in our bloodstream that works at the hemocytoblast. Remember, those are the stem cells that are the genesis of formed elements, of blood cells, okay? And in the presence of erythropoietin, it's going to cause that hemocytoblast. Remember, I said they can become any one of the three, erythrocyte, a leukocyte, or a platelet. If erythropoietin is present, it's going to cause that hemocytoblast to differentiate and become an erythrocyte, a red blood cell. Usually that's because of a diminished oxygen carrying capacity in the body. Okay. If our body isn't effectively getting enough oxygen, the kidneys will release erythropoietin into the bloodstream, and that erythropoietin will in turn stimulate the hemocytoblasts to start cranking out new blood cells as erythrocytes to shore up that deficit and increase the number of red blood cells, thereby increasing the oxygen carrying capacity. Okay, so that's what the underlying content is all about. That erythropoiesis and erythropoietin being released is regulated by a negative feedback loop. Again, if we don't have enough oxygen, erythropoietin will be released. The erythropoietin will work at the hemocytoblasts to differentiate them into erythrocytes. Once the volume of erythrocytes has been restored back to normal, then the kidneys will stop releasing erythropoietin because normal has been restored. Okay? All right, so let's talk about leukocytes a little bit, the white blood cells. Yes, sir.
Excuse me, sir.
Yes, sir.
Please, I hate to pull you back. Can you repeat that a little bit?
Of course
About
I
the
can.
release of the kidney. Sorry about that.
So the question was related to?
The release by the kidney and in response to the
Okay.
erythropoietin and the I missed the other side. Yes, sir.
Sure, of course, absolutely. All right, so if we have low blood oxygen levels, that's called hypoxia, okay? We have inadequate oxygen getting into the body. Usually that's a result of not having enough erythrocytes, not having a normal number of red blood cells to carry oxygen. So in that case, the kidneys would release that hormone called erythropoietin, and the erythropoietin would head toward the red bone marrow where new blood cells are being formed, and coming from those stem cells, hemocytoblasts, which if you remember, can become either an erythrocyte, a leukocyte, or a platelet. When that erythropoietin arrives on the scene, it's going to differentiate and steer those hemocytoblasts into becoming erythrocytes to increase the volume of red blood cells. Once those red blood cells grow in number, we have better oxygen consumption and utilization within the body. And then the kidneys will stop releasing erythropoietin because there's now a normal number of oxygen carrying erythrocytes again. Okay?
Thank you, sir.
You're very welcome.
Thank you.
All right, so leukocytes, we talked about over in lab already. These are our white blood cells. Again, very different than erythrocytes. Our red blood cells, in that they have nuclei and they have a full complement of organelles. Okay, remember, there aren't very many of them by comparison, less than 1% of total blood volume. The primary job of leukocytes, white blood cells, is to patrol through our bloodstream, through our tissues, through our cells, watching for threats. Any invaders, any abnormal substance that's made its way into the body from the external environment. Okay, and we're going to go one by one through the various types of leukocytes, and I'm going to kind of spell out and share with you what the individual types look for and do in the coming slides. But for right now, know that when we have some type of a pathogen, okay, a bacteria, a virus, a cancerous cell, anything that's a foreign invader that's a threat, our white blood cells are activated, okay, to come in and try to identify what it is first, and then secondly, to destroy it before it can take hold and get worse. All right. The second instance in the human body where white blood cells come into play is when we have inflammation. Okay. If you're walking down the street and you step off the curb and you twist your ankle and your ankle swells up very rapidly. That, of course, is inflammation. Inflammation is a protective and immediate healing effect of the body. Its purpose is to seal off the area and to try to, in a sense, contain the problem, contain the chaos to a local area. Okay? With an ankle sprain, there's really not a lot of danger that something could spread from that sprained ankle elsewhere and cause damage. But if it was a brown recluse spider that bit you with some type of toxin or a snake bite, for example, inflammation would occur. And that's where coming in and blowing up that area like a balloon is going to seal off the area and try to contain the threat to a local area and not let it spread to get worse. Okay. White blood cells, our leukocytes, are drawn to sites of inflammation via an alarm system. Okay. It's not literally an alarm, but it's a chemical alarm called chemotaxis. And that's what this underlying statement is saying. Okay. If we have trauma or a spider bite, and suddenly you have inflammation in a given region of your body, let's say in your hand, you have a spider bite, your hand is going to swell up. There are going to be chemicals called chemotaxis that are going to act as an alarm when your hand becomes inflamed and send a signal out to white blood cells to draw them to the area so that they can come into the area and start to monitor and identify what's going on. And if there's a threat, try to eradicate it before it becomes worse. Okay, so that's all I'm looking for you to understand on this underlying question here is that chemotaxis is kind of an alarm system in the event of inflammation. Inflammation always means there's some type of a problem. Chemotaxis is that alarm system, a chemical alarm that's going to attract and draw white blood cells into the area to come in and investigate what's the problem and how can we fix it. All right, so these major categories of leukocytes shouldn't be any surprise to anyone. We have the granular version, the granulocytes, and the agranular version, the agranulocytes, okay? And that again is exclusively determined by how do they look on a microscope slide, okay? Are there granules? If so, they're the granular site type. If there are no granules on the histology images, they are agranulocytes, okay? If you remember, the three fills are the granular variety, and the sites, lymphocytes and monocytes, are the agranular variety. We talked about the mnemonic to help you remember volumes of the individual types of leukocytes in our blood, starting with the highest in volume being neutrophils, N for never, the second highest being L for lymphocytes, for let, and again, the anagram is never let monkeys eat bananas. B for bananas is B for basophils. They're the least commonly occurring of the leukocyte groups. All right, we'll roll through these and we're going to go through these quick because I had you for lab and I know we've covered these in detail already. Neutrophils, these are granule. You can see the little purple granules in the microscopic image that we're looking at. The key to determining neutrophils, as we talked about in lab, is that they tend to have multi-lobed nuclei. Okay, that's usually the giveaway for neutrophils. Now, neutrophils, again, N for never, these are the most commonly occurring, the most voluminous of all of the leukocytes. Over 50%, over half of all white blood cells are neutrophils. All right, neutrophils are phagocytic cells. Okay, anytime that we talk about it, we're going to talk about phagocytic cells and macrophages often in Bio 211 throughout the course. Both of them, phagocytic cells and macrophage type cells, are garbage eaters, okay? They're going to come in and clean up a mess, all right? It doesn't mean that that's the only thing they do, but they're going to clean up debris, whether it's a dead cell, whether it's dead tissue, whether it's a virus or a bacteria or a tumor that's been destroyed. Phagocytic and macrophage type cells are going to come in and gobble it up and remove it and take it toward areas like the liver or the kidneys to get rid of it from the body. Okay, so that's what we mean by phagocytic cells or macrophage cells. All right, neutrophils, like I just said, that's not the only thing that they do, but they also can kill bacteria. Okay, so neutrophils are on patrol out in our bloodstream, watching for bacteria that may make its way into the human body. And what they do, and we'll talk more about this a week from today, next week, Thursday, when we talk about immunity, we'll talk about the very specific mechanisms involved. But they kill bacteria with what's called a respiratory burst. They actually produce substances very much like a bleach or a hydrogen peroxide that they physically inject into bacteria, which causes those bacteria to explode into tiny little particles, and then they gobble them up, ingest them, and get rid of them. Okay, so neutrophils are garbage collectors, cleanup crew, and also monitoring and killing bacteria. Eosinophils. Eosinophils, this isn't a particularly great image, but if you remember in lab, these are the ones that look like a pair of earmuffs or look like a pair of headphones typically. This one shows the two lobes of the nuclei, but it really doesn't show the band is clean. Eosinophils are going to stain, again, granular, because it's a fill. They're granular in nature. They're granulocytes, and what their job is to attack parasitic worms. If we have some type of a parasite, some type of a worm that has made it in, usually in our food products is where parasitic worms make entry into the human body. So we're usually talking about the digestive tract. These eosinophils will come on and digest their surface. And when they digest the surface and break them apart, they tend to dissolve. They also have an antihistamine-like effect, so they also help to minimize the effects of allergies and asthma. And then the last of the fills, the last of the granulocytes is the basophil, and the basophils really don't have anything visible when you look at them other than that there are a lot of granules. There's just a lot of purple granules that are very visible. All right, these are, again, using our mnemonic, never let monkeys eat bananas. Basophils are the fewest of all of the leukocyte types, okay? As it says, less than 1% of all white blood cells. These basophils contain histamine, okay? So histamine is something that causes inflammation. Antihistamines reduce inflammation caused by like allergies, for example, but a histamine causes inflammation, okay? And we talked about just a few minutes ago that inflammation is the first step in healing and repair often in the body. So histamine can be a good thing, okay? Because not only does it seal off the area like I described previously, but histamine also acts as a vasodilator. And what a vasodilator is it causes our blood vessels to dilate or to get bigger, they get wider. And when our blood vessels get wider, they allow more blood, more nutrients, more white blood cells to easily get into the area to come in and fix and make the repairs. On to the two agranulocytes, the lymphocytes and the monocytes, all right? The lymphocytes, the easiest way to explain them when looking is exactly what we're seeing here. They typically have just one very large nucleus, just like we see right here. The lymphocytes. All right, we're going to be talking a lot about the lymphocytes next time on Tuesday when we introduce the lymphatic system, and we spend a lot of time talking about the lymphatic vessels and specifically about lymph nodes. These lymphocytes tend to house themselves inside of our lymph nodes, kind of like TSA gate check guys at the airport, that as the lymph that we're going to learn about on Tuesday, liquid that's getting returned to the heart from our tissues, is passing through lymph nodes. These lymphocytes are monitoring it, again, for any type of pathogens, cancers, or foreign substances. Lymphocytes are crucial to immunity. Okay, these are our T cells that are out there fighting, trying to prevent cancers and other diseases and illnesses from taking place. Okay, they're not only in our lymph nodes, they're in our blood, they're in our spleen, they're in our tissues, but they're for the most part found in our lymph nodes. And again, you'll know all you need to know about lymphocytes and lymph nodes at the conclusion of lecture on Tuesday. And then the last one is monocytes. Okay, and again, if you remember, these are the ones that have that kidney bean shaped or C-shaped nucleus. That's usually the telltale sign when you're looking at a histology slide that you're talking about a monocyte. Okay, the monocytes are physically the largest in size, and these are macrophages. Okay, these enter into our tissues. Macrophages, remember I told you, are very much like phagocytic cells. They do the same thing. They're active phagocytic cells. Monocytes in particular work against viruses and bacteria and infections. Okay, and then not only do they monitor and fight to eradicate those threats, they also act as signaling leukocytes to the lymphocytes to come on in and help with cleanup. Okay, so that's just kind of a brief overview. Again, we're going to get more into detail on each of the leukocytes when we get to immunity 1 week from today, but kind of an introduction overview on what the individual leukocytes do. Platelets, don't really need to talk about these a lot. We talked about them in lab. Again, these are protein fragments, tiny particles that circulate in our blood. They really have one job only, and that is to form repair, to form clots if there's damage to a blood vessel. And then here's just a table that I've embedded for your study purposes of all of the formed elements, the erythrocytes, the leukocytes, as well as the platelets, talking about their volumes, their sizes, how they can be identified, and what they do functionally. Third of your quiz questions for today. Let's go back to erythropoietin, that hormone that differentiates hemocytoblasts to produce erythrocytes, red blood cells. Where is erythropoietin released from? All right, continuing. All right, blood loss. As we move into the last section, we all know that you can only lose so much blood before we get into trouble, right? The first thing that happens in a situation where we have trauma, we have disruption of a blood vessel, whether it's a vein or an artery, is the cardiovascular system, and we'll talk more about this in the next unit, but first tries to minimize blood loss on its own. It tries to protect itself, all right? And it does that by, first of all, vasoconstricting, okay? We talked about vasodilation a few minutes ago when blood vessels get larger to let more blood flow. In this case, if I'm doing dishes and I cut my hand on a sharp knife and I'm bleeding, my arteries leading toward my hand are going to vasoconstrict, the opposite of vasodilation. They're going to get very, very small. They're going to pinch off. They're going to stop blood flow or greatly reduce blood flow to the affected area to minimize blood loss. At the same time, the cardiovascular system and the blood itself, the platelets are going to head into the area and start laying down fibrin to start a clot, a patch, or repair to the damaged area. And then at the same time, they're going to signal to start ramping up production of red blood cells because we've lost red blood cells due to bleeding outside of the body. Okay, we've lost oxygen carrying capacity, particularly if a significant amount of blood has been lost. Okay, so when a human being gets to losing in excess of 15% of their total blood volume, okay, we're up to about 1 liter roughly of the 5 that we have. This is where the patient will look very obviously very pale in color. They'll be very shaky. They'll feel faint. They'll start to go into shock. Okay, they might be cold and clammy, things of that nature. Beyond that, when we get to about 1/3 of the blood loss of more than 30%, and you can see you're going to want to know this for the exam, this is where we run into life-threatening situations with shock setting in. Okay, it's at about 30% of total blood volume loss where fatal shock can incur. Okay, so when we have traumatic blood loss, we often think of transfusions, right? But the first thing to understand is that for the most part, whole blood transfusions, just a bag of blood being dumped into a patient, is extremely rare. Only when there's severe trauma and there's no other option. If you have a horrible car wreck and on the side of the highway, you're bleeding profusely, you're getting up to that 15 to 30% range. A whole blood transfusion from the paramedics can be life-saving, okay? Because you just need blood, period, okay? We're not worried about in the next couple coming slides, we're going to talk about potentially negative reactions that occur from transfusions, okay, called agglutination, okay? We're not worried about that risk if you're essentially dying anyway, okay? So in severe trauma, we may see whole blood transfusions. We also sometimes see whole blood transfusions in the situations of like armed conflict in a war. Medics are armed with whole blood transfusion because they just want to get as much blood in someone that's severely injured because it's better than nothing. Okay. Typically in healthcare, though, we don't do whole blood transfusions. If you're in the OR and you need blood, you're going to get an infusion of what's called packed red blood cells. Only the erythrocytes, the leukocytes and the plasma have been removed. Only the red blood cells are given, okay? Because after all, that's really what you need, right? You need the oxygen carrying capacity of erythrocytes. You have your own white blood cells, your own leukocytes, all right? So it's very, very important that we determine a patient's blood type by their blood grouping, their blood, whether it's A, B, AB, or O. Those are the most commonly occurring types of blood that human beings have. And because again, if we match or donate blood to the wrong blood type, we can have a fatal reaction. And that's what we're going to talk about in the next coming slides. So those blood groups, the first thing that you need to understand, and a critical thing when we talk about blood typing, is the difference between an antigen and an antibody, okay? All right, so let me start with what an antigen is. An antigen is a foreign substance that can be perceived as a threat that is on the surface of a red blood cell, on an erythrocyte. Most of us have antigens on our red blood cells, okay? So know that for the exam, what an antigen is, because not only do you need to know it for the question that you can see is underlined, but secondly, this and what an antibody is are going to help you know what blood types are and why they are what they are. Okay, so an antigen is a foreign substance, a threat that is on the surface of the erythrocyte. An antibody is something that is hunting the antigen. Okay, so the antigen is the threat, the antibody is the warrior that's hunting the antigen, the threat. All right, and if an antibody finds an antigen that's a threat, that they're opposites and it's a threat, they tend to clot and clump, and that's called agglutination. Okay, and when we have a group of red blood cells suddenly not flowing in plasma separately, but forming a snowball in your artery, it's going to block the artery, right? And nothing beyond that is going to get oxygen and it's going to die. If it happens to be in your neck, you'll have a stroke. If it happens to be in your chest, you'll have a heart attack. Okay? So that's why we don't want these. That's the potential fatal reaction that can occur if blood types are mismatched. All right, there are many more types of antigens than just A, B, and O. But A, B, and O are the big ones, okay? Those are the ones that we're worried about. So those are the type that we classify blood groups according to for human beings, okay? And then we're going to close lecture by talking about the Rh factor. All right, so I'm going to talk from this slide because as you guys know by this point, I like to lecture when you guys can see an image in front of you. The next slide is everything I'm about to say, just all written out in text. Way more confusing, at least to me it is. All right, so let's start with the easiest type, A or B. All right, let's start with A. All right, so if you are blood type A, all right, that means that you have the A antigen on your erythrocytes. Okay, remember the antigen is the foreign body, it's a threat. Okay, but not to you because you have it. All right. Therefore, the antibodies in your system, because A is all right for you, that's your normal. You're going to have antibodies flowing in your bloodstream, watching out for B antigens. So if someone with blood type A is given a transfusion of blood type B, these antibodies, which are monitoring and hunting for B, will latch on and clump them up, and we'll have a bad reaction. So therefore, a patient that has type A blood can receive, of course, type A blood because that's theirs. The antigen is fine. Their B antibody isn't going to be threatened by it. And they can also receive type O because O, as we're about to talk about, has no antigens. Okay, so B is not going to attack A, and it's not going to attack O because there are no antigens to attack. All right, so the same holds true for B. B is essentially the same thing. If you're type B blood, in this case, you just have the B antigen. So you're going to have the antibodies hunting for type A. Okay, so you then, if you have type B blood, you can receive B. And once again, you can receive O because it has no antigens. All right, then O and AB are a little bit unique, but like we've already talked about, what makes O unique is that they have no antigens. So that's why I said the vast majority of people have antigens on their red blood cells. Type O people do not. They have no antigens whatsoever. All right. So as a result of having no antigens, they have the antibodies, the warriors out searching for both A and B and would perceive either as a threat and latch onto them. So therefore, O can only receive blood type O because if they received A, B, or AB, the anti-A and anti-B antibodies would react. Okay, so they're considered a universal donor, the O type are, because they can give to everyone without threat because they have no antigens. They can only receive O. All right, the AB group, they have both antigens. on their erythrocytes, A and B, and as a result have no antibodies, the exact opposite of O. Okay, so they have no warriors, so they can receive any blood, and therefore they're a universal recipient because they don't have antibodies that are going to attack anything you give them. Okay, that's an overview of blood type and why A, B, and O exist based on the antigens and antibodies. Do we have a question?
Yes, sir.
Yes.
So question, the people with AB, does that mean that they cannot donate to other person? Like they cannot donate to A or to B?
Correct. The AB person is the only other person that could receive A and B. That is correct. Yes, because B has an anti-A, A has an anti-B, and O has an anti-A and B. So if AB donated blood to any of these other three groups, we'd have a problem. That's exactly correct. Yep.
Thank
So
you.
always just think of, remember, the blood group type determines what antigens they have. And just know they have the opposite as warriors. Okay? And you never want the two to conflict.
And Dr. Fine, just to go back to the simple analogies you used, so you said antigen would be a foreign substance or threat, and then the antibody is the one that chases or attacks that substance or threat, basically, in simple terms.
That's exactly correct. Absolutely correct. Antigens are something foreign that really shouldn't technically be in the body, and antibodies are something good, monitoring our blood, watching for threats.
Okay, thank you.
Absolutely. All right. So this slide, if you guys want to look at your own, you can, but literally this is exactly what I just told you while we were looking at the chart. I think it's way easier. All right. The other thing that I want to point out real quick, and we've already talked about this, and we talked about the various types, what type of blood they can receive. But just know for the exam that type O, again, like we said, is the universal donor because, again, they have neither A or B antigens, so they can give to anyone, but they can only receive type O because they have both A and B antibodies. Okay? So that's why sometimes, usually when you'll see like in a hurricane or some type of a big situation where the Red Cross is begging people to donate blood, usually you're going to see them first asking for people that have type O blood because type O blood people can only receive type O. They're very limited in what they can receive as a transfusion. Usually it's the first one to run up. All right.
So Doc, what about the one that say O positive and
we're going to get to that one very next. That's the very next
sir.
last slide. Yes, sir.
Okay, sir.
Absolutely. Absolutely. Nope, that's a great question and what we're going to cover. So RH is called the rhesus factor, and that is the positive or the negative assigned to your blood type. Okay, and RH stands for rhesus factor because these were experiments done in the 1940s, I believe, maybe 50s, on rhesus monkeys that scientists evaluated them to further narrow down their blood type to make it even more specific and accurate. Okay, so they conducted these experiments on rhesus monkeys, so the term is called an RH factor. These are a protein that's either there or it's not. Okay, if the RH protein is on the red blood cell, you're a positive. If the RH protein is not present on your red blood cells, you're a negative. So if you're an A, with the protein, you're going to be A positive. If you're type A but don't have the Rh protein, you're A negative. That's all the positive and negative is.
Dr. Fine.
Yes.
Since
Yes,
we're
ma'am.
going over the Rh negative and Rh positives, I am O negative, and when I was pregnant with my son, he didn't have one of the Rh antigens, and so therefore I had to receive an injection during the pregnancy. Why is that so?
I actually would not have known the answer to that question, except this morning in lecture, I had another young lady had the exact same situation. And I can't really give you the full details because she didn't elaborate, but she said that sometimes in maternity situations, when you're O negative, there is the ability for the mother's blood to attack the developing fetus's blood. So therefore, they have to have some type of an adjustment. And again, forgive me, I'm not a hematologist or an OB, but I do know, and interesting that two people, I've taught this now for 5 years. I've never had anyone. I've had two people back to back that have had this situation.
Yeah, because I was expecting twins and then lost one, and that's how we found out that I had that
Goodness.
compatibility. Yeah.
Absolutely. Yep.
Okay.
And that's what she said. They said that it really can be critical. Absolutely. Well, thank you for sharing that. Last quiz question and last slide for today. So which of the following is not a human blood type? Pretty easy one to wrap up the day, guys. All right, so I know I took some questions during lecture. Are there any additional questions on blood? As promised, I hope I delivered in that everything you ever wanted to know about blood and probably a lot more. There's a lot more to it than just red liquid, obviously.
I have a question.
Yes.
So if someone is O positive
Yes.
and someone's in the hospital, say for
Yes.
instance, and they need blood, can a person that is O negative give that person the blood as well?
Yes. Yes.
Okay.
The positive and negative, that's a great question. The positive and negative are further narrowing, kind of like on my slides, right? I give you bullet points, but then I underline some of them. I'm going to further narrow what you're doing. But the blood group itself is compatible whether it's positive or negative. But that's a great question, and I'm glad that you brought that up.
Thank you.
Absolutely. Yep. It is, again, I'm not a hematologist, but it is related to certain things. It becomes relevant. But quite honestly, I can't tell you what very specific instances, other than like what Keona shared with us, with O negative, there definitely is an adversarial relationship in that instance. So I know there are others. I just don't know what they are. Okay. So, all right, guys. Well, listen, they're talking about some horrible weather this weekend, potential. Be safe. Have a great weekend. We will see you back next Tuesday. Lymphatic system, that's an important one. We're going to cover the whole system in one day. Thursday, we do immunity, and that wraps up the content for exam 1. Don't forget, email me your 4 extra credit answers within these next 15 or so minutes. I'll send you guys the typical response that you've earned your extra credit. Stay safe, and we'll see you on Tuesday, everybody.
Dr. Fine, earlier in the
Thank
chat,
you.
you had a student ask that if our power was out, but classes weren't canceled, how do we go about that?
In that case, if classes aren't canceled and we still have weather, oftentimes I will go ahead and record the video and just send it out to the class, okay? The other option is obviously you can always, anytime, go to campus if it's convenient at the student center or the library and log on and watch. You can also take your laptop, for example, and go to Starbucks and log on. I mean, there are other options where you can connect to the internet as well, okay? But certainly if classes are canceled, then since we're a remote class, I don't want to throw our schedule off. I would obviously notify you guys. You'll get an email from me and you'll have a link. I'll record the video so we stay on track and you can watch at your convenience. Okay?
Okay, thank you.
We'll keep you posted though. But I don't anticipate anything by Tuesday, but it's a long winter still ahead of us. So, all right, guys, have an excellent weekend. We'll see you all on Tuesday.
Thank you.
Bye, guys.
Thank you.
You're all
Thank you.
welcome.